So MIT has a business school, although it's not called a business school, it's called a school of management. And what do we manage? We manage very practical things. So the next speaker, who by the way is also a European, because there's, unbeknownst to a lot of Americans, a lot of the innovation is coming from all around the world. So MIT is a global hub of sorts, and it attracts a lot of brilliant people. The next speaker has been at MIT since 1988. And he's an area of the business school which is driven by operational challenges. And he has deep experience in both statistics and mathematics, applied math, and computer science. And he's here to talk about strategic applications of analytics. He's a founder of at least 4 startups that I know. And I think he's here to explain to us not just what the innovations were behind those startups, but how it is also to work as a university professor and constantly be at the innovative edge also of commercializing technology. So without any further ado, I'm going to introduce Dimitris Bertsimas. And think of Dimitris as one of the paragons of light, sort of shining light across the MIT campus, enabling all of this innovation, because without these examples around us, I don't think the students, I don't think the labs would be able to do what it is that they do. We need these very individual examples that act as coaches and mentors. So, beyond the individual innovations that Dimitris himself represents, I think he's an example. And when you have 200 of those guys in one university campus that are shining light on different issues and are able to practice what they preach in this enormous way, that's really how you create MIT. So Dimitris, thank you.
Good morning. As you've heard, I've been at MIT. Actually, I was a doctoral student at MIT since 1985. So altogether, I've been at the Institute for about 30 plus years. And over the years, in addition to my academic activity, which is the key aspect of my life, I have also been interested on affecting the world through the use of what we develop at MIT in a variety of areas. I'm particularly excited about the innovative aspect of a startup. I don't run these companies. I have over the years several. I cannot say I know exactly the number, maybe 8 over the years, and 3 of which are currently active. Some exits in the past. So what I plan to tell you is a framework that I have developed, how to go from predictions to prescriptions, that I think is applicable very broadly, I suspect, in many of the environments that I hope you will resonate with that framework. And to motivate, so machine learning is an area that you hear a lot about, typically starts with data, and it aims to make predictions. Decisions are typically not considered so strongly. In other words, we predict things and we use the predictions, but it's not from the very beginning that we're thinking about decisions. That's the first motivation. The second motivation is the availability of data, often big data, in electronic form in massive amounts. So the question I'm asking is, can we develop, this is an academic question, but as you will immediately see, it gives rise to a variety of applications in a variety of areas. Can we develop a theory that goes from data to predictions to prescriptions, to decisions? So, and what are the attributes of such a theory? The first attribute is you would like to have, I believe, is as the data increases, the decisions you get are better and better, in fact, optimal in the limit. That is tractable, that you can actually compute in large scale, that you also have a sense of how close your solution is to the best you could possibly do. And then I would like to illustrate this framework, some examples of some companies I co-founded that are exactly based on this paradigm. And I hope I can convince you that there's no lack of examples here. So to start, I'll start with a real world problem. So imagine This is not completely imaginary. This is a real company out there. So it's a large company, global Fortune 100 multimedia company. It creates content, and it sells billions of units of entertainment media, DVDs, every year. It sells of the order of about 500,000 different titles at about 50,000 retailers worldwide. It's a global conglomerate. So this particular application happened in Europe. So this is the European environment. There were 524 stores throughout Europe that sell this type of DVDs and CDs. Huge array of potential titles. And the way it works is that you typically have a title, and in the very beginning, typically the sales are very high, and then they die quite quickly. So it's not very common to have lots of data regarding prior sales to predict the future, because the sales cycle is relatively short. So the key question is which titles to order in what quantities. And this is an example where once you produce the content, to produce the content has a sizable fixed cost, tens of millions of dollars, but the actual variable cost is cents. Because you have a DVD, you already paid for the content. So the key is the opportunity cost, that if you have the wrong things on the shelves, it's not going to do as well. So what is the big data story? So and I would also like to illustrate how the company was thinking prior to our work. So they have a lot of data. They had the sales by item and location from 2010 to present, about 50 gigabytes. And this is how the sale, this is weeks, and you see the majority of the sales is in the very beginning. Okay? This is by different titles. After 10 weeks, it more or less dies out. In addition, we also had information about the item, the title of the movie, in addition to prior sales. So some data involved the company, but a lot of, in addition to this data, there was additional data about publicly available data. For example, ratings of the movies in IMDb or Rotten Tomatoes. We had the actors, the plot summary, box office gross, whether the title has won Oscars, and so forth. There's a significant amount of publicly available data. Are we together on the application? So, and then others, for example, Google Trends. So this is an example of a Google trend in which the red is the movie Skyfall, and you see when it is announced, the trends that it generated when it's released in theaters. Huge interest in Google. And then this is when it's released in DVDs. We have this information, right? So what the internal group of the company tried to do is to try to predict sales, right? So, and they have developed weaker models than what we are saying, but they have developed models that predicted demand using some of these variables that have reasonable prediction, reasonable R squared. So these are some of the variables. For example, the search volume at release, the mean sales at location. And this was a local model for the particular store in central London. This is a model. In Hamburg, a different model, and so forth. But this was aiming at predictions, from data to predictions. The question is, but that's not what we're interested in. What we are interested in is to decide how much, from which title, to put in the shelves, right? Of course, predictions could help, but that's not the problem they were thinking about. So, and you see that the more sophisticated machine learning models, the ones that we built, start strong and stay strong. Whereas, for example, if you use prior sales and you don't use external data, you don't start well. Eventually, you do all right, but you have lost the game. So you really need the auxiliary data to do at least better predictions. But what's the general problem now? The general problem is a problem of optimization. So you have some data on the quantities of interest. In this case, demand for DVDs. You have auxiliary data that are associated covariates, actors, Google Trends, and so forth. And then you have some decisions. So what do you want to do? Given the auxiliary data, X, Google Trends, actors, and so forth, you would like to maximize the, in this case, the number of items sold, but in its full generality, you would like to optimize over Z. Z is the orders, which things to have in the cells, of some expected value, and the expected values you don't know, you only know data. So let us give you some other examples where this is not a problem only faced in this environment. So one of the companies I have founded, called Benefit Science, it has the problem of healthcare costs in the United States anyway, is about $2.5 trillion in cost. And the vast majority of healthcare is being offered by companies that insure their employees. And most of the larger companies self-insure. I would imagine, I don't know how the system is in the UK, but a large company like BT will self-insure. Is this the case here? You are not, yeah. But you know, I know, I recognize that. So what is X, what is Y, and what is Z? X, so take a company that has, let's say, 10,000 employees, one of our clients. So with 10,000 employees, about 25,000 with dependents, X is the actual claims data. When I go to the doctor, a claim is written because the doctor needs to get reimbursed. Drugs are being bought, the drugstore needs to be reimbursed, and so forth. So X is the auxiliary data regarding prior activity as seen in medical claims. Y is the future claims, the future cost, right? So a prediction problem is given prior history, how to predict Y. But what is the real problem? The real problem is how do you design the healthcare policy for the company? So what deductibles do you have? What reinsurance do you have? And so forth. So X is the past, Y is the future cost, Z is how do you design. And the company has done that, utilizing some of this technology and some others. We have figured out, we have algorithms to help companies, given this totality of data, and this is really big data, billions of records for large companies, of designing the healthcare policies in a way that optimize cost. And we have found in real world cases, in use cases, a reduction of cost for companies of the order of 10 to 20%. 10 to 20% on this. So typically, at least in the US, the first highest cost of a company is payroll, but the second highest is healthcare. So 10 to 20% on the second highest is something that the CEO pays attention. It is often hundreds of millions of dollars in costs. Large company, healthcare cost easily can be in the billions. So hundreds of millions of dollars is something that the senior management cares about. So that's an example in which this works. Let me give you another one. This is another example, but one of my favorites is personalized medicine. So let's think about that. Suppose Paul goes to the doctor. The rare times that this happens. So as you perhaps know, medicine is not personalized today. So Paul goes to the doctor, I go to the doctor. For similar symptoms, we typically get similar medicine. But so what is X? X in this case is your medical history, perhaps your genomic information as well. That's X. What is Y? Y is in a way future health, or future cost. Cost correlates with health actually quite well. So one possibility, the prediction problem, is given your medical records, given your genomic information, is to try to predict your future health, your future healthcare cost. What is Z? Z is what treatment. So if you apply these ideas, you actually have a personalized medicine story. Namely, Paul goes to the doctor. We know his own medical history. There are various treatments. Let's say the person has diabetes. So you can apply metformin. You can apply insulin or various treatments, what is the best for Paul? What is the best for me, and so forth. So in other words, I want to paint the picture that this is not, even though I put it in a context of a retail application and so forth, it's really very general. I mean, I bet if you pose a problem to me, after a minute, I will be able to put it in this framework. I spoke in the morning with my compatriot, Mr. Achilles here from BT, who works in a network environment, from what I understood in the few minutes that we talked about, where one objective is to predict traffic, but if you want to control traffic, that's the Z part. What is the X part? The X is the information you have about the network. Y is future traffic, and Z is the controls you have. They would vary. So that's a framework to think about the problem. That's why I call it a framework for innovation. All right, so I hope I convince you that this is a reasonably broad framework to think about. So, of course, given that it's a broad framework, others have thought about it. Here are the two predominant approaches. The first is what machine learning groups typically do: predict first, optimize second. So one possibility for the problem in question that I gave you, the example I gave you about the multimedia company, is you build these models. This was a random forest model. You predict demand. You predict what the demand is. You consider it as a point prediction, as a deterministic. Namely, you predict this and you expect this will happen. You optimize. So you predict what is y of x, and then you optimize. You find the z that optimizes this deterministically. Great approach, but the only problem is that it doesn't capture variability well, because you only make a point estimate. You say, I expect that the sales for the movie Enigma would be 304, but it might be 200, it might be 500. You don't take this into account. That's the disadvantage of this approach. The second approach is optimize over all what's called sample average approximation. You basically say, forget X. I'm going to take all the prior events that happened, how many sales of this movie we had in the past. That's the yi, and I find that decision that optimizes among all the possibilities. This is good in terms of variability, but doesn't appropriately account for predictability. The X disappeared here. So do people associate with what the principal methods are? Yes? Okay, so here's another method. I will give you an example to illustrate that. This is what we are proposing. And this is just, so this is to take an existing method for prediction and make it prescriptive. Imagine X1 and X2. X1, for example, could be Google Trends. X2 might be prior sales. And a blue point is in the past for that level of Google Trends and that level of sales. This is the how much sales we had in the first week. Yeah? So imagine that we are here. This is the current point we are interested. So this particular movie has this level of Google Trends and this level of sales. Of course, it's higher dimensional, it's only 2 dimensions. So what we do is we find the nearest neighbors in this X1, X2 space. We say to try to predict what will happen for this red point, find these neighbors geometrically. So there are many points, but you only take, let's say, the 10 neighbors. Okay? And then what you try to do is you try to find that decision that optimizes. These are the relevant sales, YIs. I would like to optimize that Z, this decision, that optimize only those Ys. Am I right? So nearest neighbor, this is a method that has been known for 50 years for prediction, but now we make it prescriptive. Here's another example. Decision trees. What is decision trees, for those of you who know? So you have a similar story, but now you have what's called a decision tree. You say the prediction is if X1 is smaller than 500, you do something else, and if it's bigger than 500, you do something else. You partition the space using this decision tree, and in the end, your current point is somewhere in some some partition of the space. So all the other events that are in the same partition are your neighbors. So you don't use geometry, you use what the decision tree methodology gave you. And then you say, I'm going to decide, assuming that these yi's are the relevant ones that represent me. Okay? So in other words, you take an existing methodology like decision trees, very well established, and you make it prescriptive. Yeah? And other methods. I don't have time to tell you. But back to the media example. When we approach this problem to the stores in Europe, we have found that we actually improved profitability for all European stores by 12%. 12% on about 1.4 billion sales, that's nothing to laugh about. Unfortunately, the agreement was a fixed price, not variable price. I learned better for the next time. But and the reason we achieve this is because we really focus on prescriptions, not predictions. So that's an example. In fact, this methodology is part of a company that I'm involved called Silk Route that actually installs this kind of systems using analytics for inventory management for a variety of examples. So I already told you about benefit science, in which what is Y? Y is the future medical expenses for employees. X are the claims data for employees. Z is what healthcare plans to offer. And what we have found is you can decrease healthcare costs sizably. Another example, I mean, it's even in the title, P2 Analytics. This is a consulting company I co-founded a few years back with some of my doctoral students who actually run the day-to-day. It's P2 is predictive prescriptive. So you take this idea and you apply it in a variety of contexts. We have examples from hospitals to mining to energy to fishing to financial services. This is the engagements from the last 2 years. I think it's a rather broad story. So a final remark, I would like to say, so this is impact from the university research, from papers to the real world. There's a counter effect. And the counter effect is that I have been at MIT a long time, so I actually learn from this. I actually understand, I mean, typically learning has both, it's a round trip effort, right? So you understand what the real problems are, where to focus attention, where to focus less attention. And typically the way I do this is that I learn and I create courses associated with this, and sometimes I write a book. So this is a recent book that I wrote. It's called The Analytics Edge. And each chapter is really from these experiences. Some from the companies I started and what we have learned, some of these consulting engagements and so forth. But the key aspect is that the learning enters the classroom using this type of cases. And the particular class, it's called the Analytics Edge, it has the same title, is a very popular elective, MIT-wide, attracts about 250 students in the last 2 years that we offered it. And there's a MOOC also. The MOOC attracts about 100,000 people every time it has been offered. So this is a framework from predictions to prescriptions that I think is general purpose. It is tractable. You can also mathematically prove that as the data increases, it is more and more optimal. I didn't cover that, but there is a way to assess how close to optimal it is. And I think there are a variety of opportunities in a variety of industries. I hope you got a sense of the applicability of the story. Be glad to entertain questions. Thank you.
We can take time for a couple of immediate questions, and just be prepared. If you have a question, I'm going to throw it at you. Sorry.
I hope I'm a better thrower than you, because it needs to come back to you, right? Professor, have you applied this in financial markets?
Financial markets, yes.
Can I predict stocks with your stock performance?
The key question is not whether you can predict. The key question is which stocks you buy. That's a different story.
Precisely.
And yeah.
And at what price point?
Exactly. So we have.
Turn the mic around. You have it upside down. The box is a mic.
So I will repeat the question. The question is, can we utilize this methodology in the financial services? In fact, one of the companies I'm involved, in fact, I co-founded, is called Alpha Dynamics. And it's an asset management company that really focuses not so much on minimizing the downside risk. For example, this was motivated by my experiences. In 2009, the S&P lost 43%. If a manager delivered minus 40% to the customers, he won a significant bonus that year by destroying his customers. It didn't seem correct. So I really focus on the downside risk. And with these methodologies, yes, we have. And we have delivered, in the 5 years we have been operating, what we thought we would deliver. So indeed, it's really widely applicable. You know, a machine learning model to turn it around for decisions.
Let's take another quick question. So if someone raises a hand, throw it at them.
So you mentioned that you can apply this strategy to a number of different problems, and one of the ones you mentioned was internet usage, basically on like core networks and things. Now, my thoughts on that were there are the obvious things like days of the week, time of day, etc. But things like world events and regular like election cycles might increase that usage. When you have such a large space to choose your inputs from, how do you maintain like you don't have a dimensionality explosion essentially?
These methods so machine learning is, so my premise is the following. Suppose you have a machine learning model that makes reasonably accurate predictions. That would be great, reasonably accurate. Then, using that methodology, I can use it for prescriptions, for decisions, relatively effortlessly. I have not worked in this particular application, to be honest, so I cannot tell you exactly. But if people work in machine learning or predicting traffic, the Akamai example, for example, that you try to predict traffic. So then the question is, how do you route and so forth? I think this methodology can help you. That's my point.
So you would, so you would use what they already do as a starting point and then add extra dimensionality?
Potentially, yes. That's what we have found.
Okay.
We use the experience of the company. We add publicly available data or other things that we think are relevant, but for prescriptions. Mm-hmm. So the key thing is, even if you have lousy predictions, but if they preserve the approximate order, you do fine. You might have not fantastic predictions, but they are sort of monotonically wrong. You are doing fine.
Okay, thank you.
Let's take at least one last question. Let's go down here.
So we're talking today a lot about innovation. So I'm wondering, with disruptive innovation, how do you know what X is the right X to include? Because we don't yet know how things are going to evolve.
Well, experience. So my idea is this. You use people. I have a lot of respect for people who spend all their lives in a topic. I have respect for our doctors. First of all, we already entrust our lives to them anyway. So they better know what they are doing. I use the X they think is relevant. In addition, we use our imagination. The advantage of this method is that these are potential things that matter. They don't have to be accurate. The machine learning methods are capable of detecting whether something is irrelevant or not. So basically, we use the experience plus our imagination to improve on the matter. For instance, in the example I gave you with the multimedia company, did I really know that Rotten Tomatoes would be useful? I didn't, and in the end, it wasn't that useful. But we added in, and the method selected what was relevant. And to my surprise, it selected, for example, Google Trends as one of the most important. But I did not know this a priori. So.
Perfect, thank you.
Let's roll with the punches. Let's do one more. You don't have to throw very far.
Thank you. No, so you mentioned that as long as you're not catastrophically wrong, then it's fine to be kind of on a downward trend. Are there situations in which you have been, where there's been something that the model that you apply didn't?
Not accurate. So I have applied this to about maybe 10 examples at the moment, the real world examples. They were not equally, I don't have a failure. I cannot say we applied it and what disaster it was. I cannot say that. But the relative success was different. You know, in the examples I gave you, 12%. In the benefit science example, so far our improvements have been 10 to 20, but there were situations that the improvement was marginal, 1 or 2%. I'm not saying it works for everything. I mean, you know, if somebody makes this claim, I'm doubtful. But I do believe that it gives you a new way, it gives you new policies that you have not thought of. So as a disruptive innovation, that's why I chose the topic, actually. So I find it useful. And I'll tell you an experience with recently we actually published a paper in Diabetes Care about personalized medicine, in which, so I lost my mother to diabetes, I care about this disease. So I have found that I'll give you an example of a very unusual proposal it made. So I bet there's somebody in this room who is diabetic. It's young people, but primarily, I know the statistics. Huh? So as diabetes evolves, you get people use insulin, right? So the models, for some people, it selected and said people who use insulin use metformin. Very unusual. Why? To use insulin is a complicated thing. You have to measure, you have to anticipate what you eat and so forth. And what it detected is that these people were not using insulin correctly. It wasn't that insulin is a bad thing. It understood from the data a behavioral pattern that is not effective to them. And said, okay, maybe we are not using the strongest drug that you can use a weaker drug, but it's just a pill. And for those people, might be helpful. And we've tried it. It wasn't successful on all of them, but on average, it improved the glucose level. So this is something that I don't believe a doctor would easily do. To be honest, I know so, because the data suggests they never do it. If somebody tries insulin, takes insulin for the rest of their life, but the algorithm detected the behavioral pattern. Am I making sense?
Do you still have your question over there? Do you have your question? This is something I rarely do. We are a little after schedule, but this thing just is too fun to let up. I love this thing. So let's do one more.
Thank you. The question is just a bit more general. What, in your experience in the last 5-10 years, how has machine learning evolved beyond the availability of a lot of data and the fact that there's a much better computing?
Yeah.
What's your sense of that?
I mean, I'm very bullish on this area. I devote why. So the two reasons is the one you mentioned. The gigantic availability of data. The good example of that is computer vision. Computer vision, it's present with deep learning and neural networks 20 years ago. Same methods were used. Failure. It was not successful. And it was not successful because the data that is being used was roughly, we trained 10 to the 5, about 100,000 examples to train. Unsuccessful. Recently, when the data to train was 10 to the 9, success. We are about to have driverless cars. We actually have driverless cars moving around. What really happened? Then the size increased a little bit, maybe a factor of 2, a factor of 3, but the data increased 4 or 5 magnitudes. So the same method was used. So you say, what's the innovation? The innovation was primarily the data and the computing power. But it's not only that. In some of the work we are doing at the moment, in my group at MIT, we have developed new algorithms that actually are strong, at least in examples in academic environment, are stronger than neural networks. Sizably stronger on applications that the neural networks have not been so successful. I'm not 100% of the statement, otherwise I've been talking about that, but I see a lot of evidence of that. So I would say it's data, machines, and improve experience and intelligence of humans. So all of them are moving in the right direction. So I'm optimistic that we could solve problems that we would not be able to solve before. Like cancer, like diabetes, like name it.
We're not going to lose this thread. This is a good start.